assembling and selecting chains of blocks. The final step in Bitcoin's decentralized consensus mechanism is the assembly of blocks into chains and the selection of the chain with the most proof of work. Once a node has validated a new block, it will then attempt to assemble a chain by connecting the block to the existing blockchain. Nodes maintain three sets of blocks: those connected to the main blockchain, those that form branches of the main blockchain, secondary chains, and finally blocks that do not have a known parent in the known chains, orphans. Invalid blocks are rejected as soon as any one of the validation criteria fails, and are therefore not included in any chain. The main chain at any time is whichever valid chain of blocks has the most cumulative proof of work associated with it. Under most circumstances, this is also the chain with the most blocks in it, unless there are two equal length chains and one has more proof of work. The main chain will also have branches with blocks that are siblings to the blocks on the main chain. These blocks are valid but not part of the main chain. They are kept for future reference in case one of the chains is extended to exceed the main chain in work. In the next section, we'll see how secondary chains occur as a result of an almost simultaneous mining of blocks at the same height. When a new block is received, a node will try to slot it into the existing blockchain. The node will look at the block's previous block hash field, which is the reference to the block's parent. Then the node will attempt to find the parent in the existing blockchain. Most of the time, the parent will be the tip of the main chain, meaning this new block extends the main chain. For example, the new block 277316 has a reference to the hash of its parent block 277315. Most nodes that receive 277316 will already have a block 277315 at the tip of their main chain and will therefore link the new block and extend the chain. Sometimes, as we will see in blockchain forks, the new block extends a chain that is not the main chain. In that case, the node will attach the new block to the secondary chain it extends and then compare the work of the secondary chain to the main chain. If the secondary chain has more cumulative work than the main chain, the node will reconverge to the secondary chain, meaning it will select the secondary chain as its new main chain, making the old main chain a secondary chain. If the node is a miner, it will now construct a block extending this new longer chain. If a valid block is received and no parent is found in the existing chains, that block is considered an orphan. Orphan blocks are saved in the orphan block pool, where they will stay until their parent is received. Once the parent is received and linked into the existing chains, the orphan can be pulled out of the orphan pool and linked to the parent, making it part of a chain. Orphan blocks usually occur when two blocks that were mined within a short time of each other are received in reverse order, child before parent. By selecting the greatest cumulative work valid chain, all nodes eventually achieve nationwide consensus. Temporary discrepancies between chains are resolved eventually as more work is added, extending one of the possible chains. Mining nodes vote with their mining power by choosing which chain to extend by mining the next block. When they mine a new block and extend the chain, the new block itself represents their vote. In the next section, we'll look at how discrepancies between the competing chains forks are resolved by the independent selection of the greatest cumulative work chain. Blockchain forks. Because the blockchain is a decentralized data structure, different copies of it are not always consistent. Blocks might arrive at different nodes at different times, causing the nodes to have different perspectives of the blockchain. To resolve this, each node always selects and attempts to extend the chain of blocks that represents the most proof of work, also known as the longest chain or greatest cumulative work chain. By summing the work recorded in each block in a chain, a node can calculate the total amount of work that has been expanded to create that chain. As long as all nodes select the greatest cumulative work chain, the global Bitcoin network eventually converges to a consistent state. Forks occur as temporary inconsistencies between versions of the blockchain, which are resolved by eventual reconvergence as more blocks are added to one of the forks. In the next section, few diagrams, we will progress of a fork event across the network. The diagram is a simplified representation of the Bitcoin network. For illustration purposes, different blocks are shown as different shapes: star, triangle, upside down triangle, rhombus, spreading across the network. Each node in the network is represented as a circle. Each node has its own perspective of the global blockchain. As each node receives blocks from its neighbors, it updates its own copy of the blockchain, selecting the greatest cumulative work chain. For illustration purposes, each node contains a shape that represents the block that it believes is currently the tip of the main chain. So if you see a star shape in the node, that means that the star block is the tip of the main chain as far as the node is concerned. In the first diagram, figure 10.2, the network has a unified perspective of the blockchain with the star block as the tip of the main chain. A fork occurs whenever there are two candidate blocks competing to form the longest blockchain. This occurs under normal conditions whenever two miners solve the proof of work algorithm within a short period of time from each other. As both miners discover a solution for their respective candidate blocks, they immediately broadcast their own winning block to their immediate neighbors, who begin propagating the block across the network. Each node that receives a valid block will incorporate it into its blockchain, extending the blockchain by one block. If that node later sees another candidate block extending the same parent, it connects the second candidate on a secondary chain. As a result, some nodes will see one candidate block first, while other nodes will see other candidate block, and two competing versions of the blockchain will emerge. In figure 10.3, we see two miners, node X and node Y, who mine two different blocks almost simultaneously. Both of these blocks are children of the star block and extend the chain by building on top of the star block. To help us track it, one is visualized as a triangle block originating from node X, and the other is shown as an upside down triangle originating from node Y. Let's assume, for example, that the miner node X finds a proof of work solution for a block triangle that extends the blockchain. Building on top of that parent block star almost simultaneously, the miner node Y, who was also extending the chain from block star, finds a solution for block upside down triangle, but his candidate block. Now there are two possible blocks. One we call triangle originating in node X, and one we call upside down triangle originating in node Y. Both blocks are valid. Both blocks contain a valid solution to the proof of work, and both blocks extend the same parent block star. Both blocks likely contain most of the same transactions, with only perhaps a few differences in order of transactions. As the two blocks propagate, some nodes receive block triangle first and receive block upside down triangle first. As shown in figure 10.4, the network splits into two different perspectives of the blockchain, one side topped with a triangle block, the other with the upside down triangle block. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.